Chapter 3, Lesson 3 is titled Compounds and Mixtures. It can be found on page 87 in your textbook. Our objectives for today are listed on the right-hand side of that page. Scholars will identify the characteristics of a compound. Scholars will compare and contrast different types of mixtures. On page 87, we begin learning of substances. Scientists classify matter in several ways that depend on what it's made of and how it behaves. For example, matter that has the same composition and properties throughout is called a substance. Matter that has the same composition and properties throughout. Elements such as a bar of gold or a sheet of aluminum are substances. When different elements combine, other substances are formed. What are those things called when you have multiple elements that combine? So there's basically two types of substances. One is an element in which you have a substance with one type of atom, so it's all the same thing. Or a compound is a substance made of atoms of more than one element bonded together. So you might have hydrogen and oxygen as an element. That's an example of a substance in our world. You might put those two things together and get water as an example. H2O, two hydrogen molecules and one oxygen molecule is considered a compound. So you still have what's considered a substance. They're still the same throughout, except one is made up of one type of atom and one is made up of another type of atom. Example, gold is a substance, it's an element. Aluminum is a substance, that's an element. Basically anything that's on our periodic table would be considered a substance as an element. And then when you put some of those items on our periodic table together by some of the natural reactions that happen, you get these combinations or compounds. Water is H2O and then hydrogen peroxide, H2O2. Time for a joke. Two friends walk into the restaurant and the first person orders a water. He says, "I'll have an H2O." Second friend says, "I'll have an H2O2, please." After drinking the beverage, the second man died. Mr. Shane, that's not very funny. Well, why did he die? An H2O is a water, and H2O2 is hydrogen peroxide, and that's actually quite toxic. It might be used to kind of clean out your cuts or to sterilize something, but it's actually really, really dangerous. But did you notice what he said? First person says, "I'll have an H2O," which means water, two hydrogens, one oxygen. The second person says, "I'll have an H2O2. Two oxygens makes it hydrogen peroxide, and therefore when he drank that, that was real dangerous." Good thing it was just a joke. Compounds. What do you call the colorless liquid that flows from the kitchen faucet? You probably call it water, but maybe you've written it as H2O. The element hydrogen and oxygen exist as separate colorless gases. However, these two elements can combine as shown in figure 18 to form the compound water, which is a different form of an element that makes it up. A compound is a substance whose smallest unit is made up of atoms of more than one element bonded together. Substance whose smallest unit is made up of atoms of more than one element bonded together. Compounds often have properties that are different from the elements that make them up. Water is distinctly different from the elements that make it up. It is also different from other compounds that are made from the same elements. Have you ever used hydrogen peroxide? Here it is again, to disinfect a cut. This compound is a different combination of hydrogen and oxygen and has different properties than those of water. Water is a non-irritating liquid that is used for bathing, drinking, cooking, and much more. In contrast, hydrogen peroxide carries warnings on its label such as "Keep hydrogen peroxide out of your eyes." Although it is useful in solution for cleaning contact lenses, it is not safe for your eyes as it comes from the bottle. It's also not safe to digest either. Compounds have formulas. What's the difference between water and hydrogen peroxide? H2O is the chemical formula for water, and H2O2 is the formula for hydrogen peroxide. The formula tells you which elements make up a compound as well as how many atoms of each element are present. Look at figure 19. The subscript written below to the right of each element's symbol tells you how many atoms of the element exist in one unit of that compound. For example, hydrogen peroxide has 2 atoms of hydrogen because it says H2 and 2 atoms of oxygen because it says O2. Water is made up of 2 atoms of hydrogen and 1 atom of oxygen. So the chemical formula tells you which elements make up a compound as well as how many atoms there are. The little number written below is called the subscript. It tells you how many atoms in that element are in the compound itself. Carbon dioxide, CO2, is another common compound. Carbon dioxide is made up of 1 atom of carbon and 2 atoms of oxygen. Carbon dioxide is what we breathe out after we've taken in oxygen. What we're expelling when we're breathing out, that's CO2. Carbon dioxide is made up of 1 atom of carbon and 2 atoms of oxygen. Carbon and oxygen also can form the compound carbon monoxide. CO, which is a gas that is poisonous to all warm-blooded animals. Carbon monoxide is often a gas that you're going to see or smell maybe coming out of the exhaust of a car. And if you're breathing that in, it's actually really dangerous. In your house, you probably have a carbon monoxide detector because your water heater or some of the equipment that's keeping your house running might expel carbon monoxide as it's running. So your house has to have a detector. It's probably right with your fire alarm detector to say, is this here? Because you actually can't smell it. And people have died from carbon monoxide because you can't smell it. All of a sudden you just get dizzy and you pass out because it's odorless and poisonous and can cause death. As you can see, no subscript is used when only one atom of an element is present. A given compound always is made up of the same elements in the same proportion. For example, water always has 2 hydrogen atoms for every oxygen atom, no matter what the source of the water is. No matter what quantity of the compound you have, the formula of the compound always remains the same. If you have 12 atoms of hydrogen and 6 atoms of oxygen, the compound is written H2O, but you have 6 molecules of H2O, so you put the 6 out in front like a coefficient, and not H12O6. The formula of a compound communicates its identity and the makeup to any scientist in the world. So no subscript is used when only one atom of the element is present, and a given compound is always made of the same elements in the same proportion. You don't just add numbers to the subscripts in order to say that, well, there's more of these water molecules. You actually add the number in front, as shown on page 88. 6 H2O molecules would tell you that you've got those 12 hydrogen atoms and 6 oxygen atoms. So you'll just write H12O6. Here's an example. What we would want to learn how to do is to make sure we understand the number of elements that are in each compound. Here it says H2, that's hydrogen. That means there's 2 hydrogens and 1 oxygen. In hydrogen peroxide, there's 2 hydrogens and 2 oxygens. There's a difference there. Carbon dioxide, what we're breathing out, has 1 carbon. If nothing's listed here, it just means 1. And O2 means that there's 2. Carbon monoxide, mono, means 1. So you have 1 carbon and 1 oxygen. Mixtures. When 2 or more substances come together but don't combine to make a new substance, a mixture is a result. Unlike compounds, and proportions of the substance in a mixture can be changed without changing the identity of the mixture. For example, if you put some sand in a bucket of water, you have a mixture of sand and water. If you add more sand or more water, it's still a mixture of sand and water. Its identity has not changed. Air is another mixture. Air is a mixture of nitrogen, oxygen, and other gases which can vary at different times and places. Whatever the proportion of gases is still in the air. Even our blood is a mixture that can be separated as shown in figure 20 by a machine called a centrifuge. The interesting thing about air, we often think that, well, we need oxygen to survive because that's what our lungs are taking in. That's what's going to supply all of our muscles and our brain with the necessary means to survive. Oxygen actually doesn't make up the greatest percentage of the air. Nitrogen actually is the greatest prevalent gas in the air. It's about 70% of what we breathe, and oxygen is somewhere between the 20 and 23%, with a number of the other gases that are in the air floating around as well. But that 20% is what we need to survive that oxygen, where we often don't think about that in the mixture of air that we're breathing in. Your blood is a mixture made up of elements and compounds. It contains white blood cells and red blood cells, water, and a number of dissolved substances. The different parts of blood can be separated and used by doctors in different ways. The proportions of the substances in your blood change daily, but the mixture does not change in its identity. So, mixtures, unlike in compounds, they've got proportions of the substance. They can be changed without changing the identity of the mixture. Basically, the mixture is the different ingredients that might be put into something that don't necessarily go together, or they can be separated in a way. In the examples here, air and blood, you've got different substances coming together to form a new substance. But you can also separate those things into their original pure substances. Separating mixtures at the bottom of page 90. Sometimes you can use a liquid to separate a mixture of solids. For example, if you add water to a mix of sugar and sand, only the sugar dissolves in the water. The sand then can be separated from the sugar and water by pouring the mixture through a filter. Heating in the remaining solution will separate the water from the sugar. If you boiled off the water, the sugar would remain. It would become undissolved as the water would disappear or turn into steam. The sugar would be left in that container that you're boiling. Heating the remaining solution would separate the water from the sugar. At other times, separating a mixture of solids of different sizes might be easier, as pouring them through successively smaller sieves or filters. a mixture of marbles, pebbles, and sand can be separated in this way. Maybe when you're cooking noodles, you've got to separate the water that you've boiled to cook those noodles from the noodles themselves. You're going to put them through a strainer. It's kind of the example of separating a solid from a liquid. Unless that solid gets actually dissolved inside that item, then you've got to completely boil that material off in order to get to it. So mixtures can be separated easily. When they're put together, it might look like they're being added together. Say, for example, if you're making Kool-Aid. You're putting the Kool-Aid packet in, you're putting the amount of sugar in, and then you're putting the water in, and all those things mix together and they form this new mixture, this new substance. It's not a pure substance because you can actually separate those things out. If you scientifically had the right means, you could boil off the water and separate the sugar, and then somehow separate the sugar molecules from what would have been the Kool-Aid recipe as well. There are two types of mixtures, homogeneous and heterogeneous mixtures. Homogeneous mixtures are the same, and heterogeneous mixtures are different. Let's take a look at how these things play out into our definitions of mixtures, and we'll actually look at some of the pictures that are on the page 90 and 91. Mixtures such as the one shown in figure 21 can be classified as homogeneous or heterogeneous. Homogeneous means the same throughout. You can't see the different parts in this type of mixture. In fact, you might not always know that homogeneous mixtures are mixtures because you can't tell by looking. Which mixtures in figure 21 are homogeneous? Homogeneous, you'd have the picture of the Kool-Aid. It's the same throughout. The first sip at the top of the glass of that Kool-Aid is going to be the same as the bottom of that Kool-Aid. Basically, anything that you're going to be drinking should be considered a homogeneous mixture. Otherwise, I wouldn't be drinking it because it's probably not very good for you. Like if you take a drink of a glass of milk, it should be the same at the top than it is at the bottom. You shouldn't have like the thick part of the milk on top or the thin part of the milk on the bottom. If you're drinking soda, it should be the same soda all the way throughout. Anything that's in that liquid form that we're drinking a lot of times is considered a homogeneous mixture because different ingredients went into making that, but it should be the same throughout. So the Kool-Aid is an example of a homogeneous mixture, and then the blanket itself. It's a mixture of different fabrics that are woven together. You can't really tell that they're different fabrics, but if you looked at the tag on maybe a piece of clothing or something that shows the different fabrics that are woven together, it might say a percentage of cotton, a percentage of polyester. That's the same throughout, but it might have two different ingredients or two different things that are put together. No matter how closely you look, you can't see the individual parts that make up air or the parts mixture called brass in this lamp. In the lamp itself, you've got one entire piece of metal. That's brass. It actually has different types of metal that put together to make that type of metal. It's called an alloy. Homogeneous mixtures can be solids, liquids, or gases. A heterogeneous mixture has larger parts that are different from each other. You can see the different parts of heterogeneous mixtures such as sand and water. How many heterogeneous mixtures are in figure 21? Well, the salad is heterogeneous because there's salad. In terms of the lettuce, there's peppers, there's cucumbers in there, so those are different pieces in the salad that you can see. In the rock, the piece of granite, you can see the different types of rock that are in there to give those different colors. In the piece of parchment or that kind of light colored thing that's laying down right there, you can see the different pieces or the different parts of it as they have those different colors. Another really good example is pizza. If you've got pizza with different ingredients, you've got the dough, you've got the sauce, you got the cheese, and then you've got your toppings. All those different things, you can see those different parts. That's an example of a heterogeneous mixture. A pepperoni and mushroom pizza is a tasty kind of heterogeneous mixture. Other examples of this kind of mixture include tacos, vegetable soup, a toy box full of toys, or a toy toolbox full of nuts and bolts. Anytime that you can see the different parts, that's considered heterogeneous. Anytime you can't see those different parts, it's considered homogeneous. That wraps up our study in what would be Chapter 3, Section 3, Compounds and Mixtures. Please make sure that you've completed your notes, and good luck with your reinforcement.